My name is Qihong. You can also know me by Lorena or Chi. Every one of you know me by different names, but I will reply to all of them. I'm a second year PhD student in the group of experimental aerodynamics and propulsion under the supervision of Andrea Ianniro and Stefano Dicetti. And I'm gonna explain you or try to do it in 10 minutes what I am doing in my thesis and what I've done in these 2 years. I will try to keep it simple so that it is easy to digest before the lunch. So I want to start saying that turbulence is everywhere. And we can find it in canonical forms such as in wake flows, turbulent boundary layers, jet flows, or mixing layers. But apart from these canonical textbook flows, which also appear in real life, we can find it in many, many situations in our daily lives, from transportation, combustion chambers, even in the coffees we take in the morning and in the meriendas in the afternoon. So we can understand that it is very important to study and understand turbulent flows. And this is great because we know that analytically they are described by the Navier-Stokes equation. We want to look for dynamical models in order to understand this interaction between the devices or vehicles with these turbulent flows. And also we want to control them because, of course, we want to improve the efficiency of the devices, reduce the drag, reduce fuel consumptions, and other objectives. But not everything is so nice because otherwise I wouldn't be here doing this thesis, and we have, of course, some limitations. So first of all, I want to mention that the Navier-Stokes equations do not have an analytical solution. We should rely on simulations, but I think many of you know already that it is quite complex. We know that turbulent flows are very nonlinear and very, very high dimensional, meaning that it is very difficult to work with them. So in case you want to avoid simulations and you want to try experimental measurements, good luck, because as Luca mentioned before, we also have technological limitations. And we want to look for simplified ways in order to model these dynamics. And here's where I enter my thesis, which is called Data-Driven Modeling of Turbulent Flows Under Active Flow Control. But I like to summarize it as me trying to get reduced order models from experimental measurements. Reduced order because I want to avoid this high dimensionality, and data-driven because it's gonna be it's gonna be obtained from experimental measurements. So during the first year, I've been doing an extensive literature review, first of all on dimensionality reduction, with the objective of understanding how to study these coherent structures that we can find in turbulent flows, and also taking advantage of maybe modeling the dynamics of turbulent flows with low-dimensional attractors and extract dynamical models from experimental measurements, such as PIV, to obtain velocity field measurements. To give you one of them, I'm going to focus on proper orthogonal decomposition, or POD, which is the main one I use, and consists in the following. I present you Thea, and I want to do a drawing of her. So if I want to do a realistic drawing, representation is quite difficult, but I can keep it simple and maybe draw the main features, so the main geometries. This would be equivalent to do a reconstruction with the main modes, so main patterns that are the most energetic ones. But I can add more and more details until I get to a more realistic representation. I can also do this with fluid flows. I present you here an example of the wake of a cylinder, and if I apply the POD, if I compute the POD, the proper orthogonal decomposition, I can get spatial modes, which are equivalent to these patterns that I was mentioning when I was trying to draw Thea. Then the singular values, which are gonna give me the weighting, so the energy or how relevant are each of these modes. To give you an example, it's like a more energetic mode would correspond to the round shape of the head, and a less energetic mode would be a wrinkle in the forehead, for instance. And a very important characteristic is that they are ordered from most energetic to less. And finally, the temporal modes, because here I have a flow that is evolving in time, and of course I want to know how each of these modes is gonna evolve in time. So this give me the temporal history. Then I continue the literature review with data-driven models, where I include also nonlinear systems identification, and I can categorize the models in 3 different categories. So the first one would be white boxes, which basically consist on solving the Navier-Stokes equations, or simulating the Navier-Stokes equations. Then we have black boxes, which consist on training with machine learning a model where I only look for an input-output relationship without knowing any physics or anything inside the box. And finally, the gray box, which combines reduced order modeling, so keeping the main modes of the system together with the knowledge of the physics, because as I mentioned, we know that the dynamics are modeled by the Navier-Stokes equations. Although it is very tentative to use black boxes because they are quite popular lately, it has been observed that neural networks work. We want to take advantage of the knowledge of the physics, and that's why my thesis is marked into these type of models. This is the objective of the first work I've done in the first year, which follows the following idea. So here we see a man that is running, and from our observations, our knowledge of the physics, we know that if I fix a frame here, seeing the position of the man, that he's slightly inclined forward, that he's standing on the tip of the left foot, he's raising the right leg, we can somehow predict what is going to happen in few instants after this image. And he's going to do a step forward. And indeed, he does that. So the meaning behind this is that with the knowledge of the physics, we can somehow predict what is going to happen in short periods of time. And this is what we want to apply to turbulent flows, with the knowledge of the Navier-Stokes equations, which are going to give me the knowledge of the physics. This is the objective of the first work, which consists of a Galerkin model, where I start with full flow fields, which are very high dimensional, as I mentioned before. I decompose it into modes, following, for instance, PhD, as I explained at the beginning. I simplify the model, and I will give you a slight hint later, and then I reconstruct the dynamics. So behind each of these boxes, we have, at the beginning, experimental measurements with PIV, so I get velocity fields, and they are non-time resolved, and in this case, it's of experimental jet flow. I continue with the POD decomposition, and now the key part of the model, sorry, it's a bit messed up. It's a Galerkin model, which basically I take the Navier-Stokes equations, I project them into a truncated set of spatial modes I obtained before, and I get a simplified model, and later I can reconstruct the dynamics. I can show you here some, first of all, I want to remark that the main advantage of this model is that I don't need time resolution. So the meaning is that I just need some snapshots, and with my model, I am gonna recover the dynamics of what is happening in the middle. To show you some examples, I've been tested different snapshot separations, so increasing the temporal separation every time, until I reach this point where I'm gonna show you the reconstruction. This consists of snapshots separated by several convective times, so in this case 1.6, and I get the reconstructed velocity fields. So on top, I have the reference, which is gonna be my low-order reconstruction. In the middle, I have the interpolation, which simply consists of the reconstruction of the flow fields with the interpolation between the given snapshots. And the main result that we can see here is that the case of the interpolation, it's failing. It's not able to capture the convection of the flow downstream. And also it's kind of creating structures that appear and disappear that are not physical. On the other hand, we have here the reconstruction with the Galerkin model, and it convex correctly the flow downwards, and it reconstructs the structure according to the lower, compared to the reference, which is the lower reconstruction on top. So at the beginning of the second year, I finalized this work on the Galerkin model. I prepared a journal paper, which is now under review, and I continue with three different paths. So the first one, it's a meshless approach, a meshless Galerkin model, which targets spatiotemporal modeling of the flow, not only temporal, as I was mentioning before. And this is a collaboration with Jacopo, who is a PhD student I hope you all of you know. He's gonna defend his thesis next Monday, so in case you wanna go, you can join. And this model is based on the work of meshless POD that Jacopo developed together with Miguel, that is here in the crowd. The second work, it's a multi-manifold approach, where basically I want to tackle the problem of multiscality of turbulent flows. So when I am performing a global decomposition, I am missing the smaller scales, the smaller scale structures. Therefore, the objective of this work is to do local decomposition. So find the dynamics locally so that I can focus on the main structures in each of these regions of the flow. And this is a collaboration with Guy, a postdoctoral fellow here at UC3M. And finally, a hybrid model for controlled flow, which is a new work at the very beginning, which is a collaboration with a professor, with the professor Scott Dawson in the University of Illinois. And hopefully this would lead me to my research stay in the third year. To show you some contributions, I show you here the first journal article I've written, which, as I mentioned, is under review. Some conference contributions, courses and workshops that I have attended, and many disseminations activities that I've done mainly with Luca for European Night or Week of Science. To recap and show you the future activities I am planning to do, in the first year I've done the literature review to understand what I have to do and what has been done before. I've developed the first model, which consists of the Galerkin model. In the second year, I've finalized the journal paper of the Galerkin model, and I'm waiting for the response of the reviewers. And I've started 2 different works. The first one seeking for a spatiotemporal modeling, and the second one looking for local representation of the dynamics, and a collaboration which might lead, hopefully, for the research stay in the third year and the publication of the new works I've started. Finally, I hope to defend at the end of the third and the beginning of the fourth year. So this is all from my side. I hope it was not too boring. I hope you like it. And if you have any question, I will be here to answer.
Thank you.